Thanks, Doug. I don't know about that, but I'm grateful for the opportunity to speak with you all about modeling stress waves in snow. And so why would you want to model stress waves through snow and through the slab? Well, many avalanches start from some impact. That impact could be a cornice fall, a skier, snowmobiler, explosive. But any impact is going to send stress waves through the snow and create a dynamic stress bulb that's going to reflect and refract through different layers and could break a weak layer. And if you know how that stress wave's moving and the strength of your weak layer, you'll have an initial crack size. You could then ask a question about propagation, but we're talking about the initiation stage here. With a good stress wave model, you could also better understand the effect of isolating your compression test or extended column test or Roosh block, some impact type of stability test, the effect of isolating those sides. And then down the road, you could implement a stress wave model into a snow cover model like snowpack, whereas if you had simulated stratigraphy with different densities and hardnesses, you could say a skier impacts the top of the snow like this, so then we expect the stress wave to go through this simulated stratigraphy and we expect to see a crack this size. Or an explosive hits the top of the snow like this. This is how that stress wave is going to go through the snow. I'm not going to answer all these questions today. There's a lot of questions. But a stress wave model is foundational to these sorts of questions. And so I'm going to talk about my efforts in modeling the stress wave. So how could you model a wave? Well, there's this famous wave equation there's a famous equation called the wave equation. Physicists use it to model electromagnetic waves, like radio waves and light waves, and it describes how the electric field and magnetic field go through space at the speed of light. When you pluck a guitar string of a certain temperature or certain tension, diameter, and material, the wave equation predicts the frequency that it will go at. And that will send sound waves through the air. Those sound waves will bounce off walls, and the wave equation describes that behavior as well. Also, earthquakes can be described with the wave equation. So lots of different types of waves can be described with this. A subset of the type of waves that you can describe are pressure waves. And these are the type of waves that happen when a hammer hits a nail. Sound waves are pressure waves. And they can go through, solids, liquids, or gases. The movie here, there's some impact hitting the left side. Let me get a little pointer. So there's some impact hitting the left side here. And that will send that pressure wave through whatever material it is. You know, if it's a hammer hitting a nail, that stress wave goes through the nail and then breaks the wood below it. Just like how something hitting the top of a hard slab would go through that hard slab and then break the weak layer below it. And so an important characteristic of these pressure waves is the direction of wave propagation. I'm not talking about crack propagation here. Like the direction of the wave front is moving from left to right here. And any individual particle within this medium is also moving left to right. Whereas like a guitar string is the opposite. You pluck it one way and then that wave goes up and down and the direction of propagation is left to right. So these are the type of waves that I'm going to focus on with the wave equation. And so warning, if you're not into equations, there's one coming up, but I feel obligated to show it. Feel free to space out for a minute if you'd like. But this is the wave equation.
This is why you're going first, too. So get this out of
Yeah, everyone's had their coffee. They can handle 3 terms in an equation. The first term is how the displacement of something changes with time. And that's related to how the displacement of something changes with space. And it's related by the wave speed. So if we're talking about sound waves, this is the speed of sound. If we're talking about light waves, this is the speed of light, and it's not displacement, but it's electromagnetism. But pressure waves through a solid medium, this is related to the elastic modulus and density. It's like the equivalent of the speed of sound in air, but through something like snow. We all know density. Some of us know elastic modulus, but this term describes how stiff something is. If you push on something, how much it will deform before it rebounds elastically. So something like concrete is pretty stiff. Something like wood's a little less stiff. Concrete has a higher elastic modulus than wood. And so it's important that the wave speed is only a function of these two variables, because if we can measure the wave speed and if we can measure the density, then we can estimate what the elastic modulus is. And so I've done that in some experiments. So on to the hypothesis that I have for part of my research, and that's that the wave equation effectively models a stress wave through hard slabs. So I wanted to test this hypothesis in the sub-zero lab and build a bunch of hard slabs. The general experimental design is to have two columns of snow. The column on the left is dedicated for snow property measurements like density, temperature, hand hardness, etc. And the column on the right is for impact testing. So this is what the columns look like in the lab. I did them compression test size because we're all familiar with compression tests. And I did impacts that are like the wrist, elbow, and shoulder taps, but I dropped a known weight from a known height instead. And then I put a whole bunch of sensors in these columns as well. So here's a top-down view looking into the mold as I'm sifting up these columns. And I embedded these wireless accelerometers, so they measure acceleration. And shout out to James Lesser, who made these for his master's degree. He did a great job making these really cool, this cool system, this network of accelerometers that you can put in the field, in the lab, whatever, and measure how the snow moves. So as I'm sifting the column, I'm laying down these accelerometers at 3 different heights. If the font's too small, we're at 10 centimeters, 30 centimeters, and 50 centimeters, and have 2 of them side by side. So those are the measurements within the snow, measuring acceleration. And then the boundaries of the snow, the top and the bottom, also measuring acceleration, which I've got accelerometers mounted to these aluminum plates. And then in addition, I'm measuring stress, which is kind of like using a bathroom scale. You stand on it and it gives you a weight. Weight over some area is the stress. So these are kind of like glorified bathroom scales that measure really quickly and also measure acceleration at the top and the bottom of the column. So that's the experimental setup to test the hypothesis. And here's what we expect to happen. So I'm going to impact the top of the column with that dropped weight. And we're looking at both stress and acceleration. And these graphs here, what happened to my mouse? These graphs are oriented where the y-axis, the vertical axis, is height. So it's a 60 centimeter high column. And then the horizontal axis is either stress or acceleration. So let me play this movie. All right. So as you hit it, this stress wave's coming down. And so we've got peak impact right here because that stress is peaked out. And then, let's try that again. All right. So we hit it. It reaches the peak. And then this dropped weight bounces off of it. The column's no longer being stressed. And we have this stress wave that's going down. And so that stress wave's going down the column. The snow's accelerating and decelerating and going back to rest. And then something really interesting happens at the bottom because I'm on this reinforced concrete floor, there's very little motion. And it's kind of like you hit a piece of rebar right into rock. It's going to shoot that stress wave right back up. And you get a reflection off the bottom, and that stress wave doubles up. So you sent something at 1 Pascal down, it's going to reflect off the bottom perfectly and hit 2 Pascals at the bottom, which is interesting because if you have some bed surface that's really hard, that stress wave could be magnified because of the reflection. And I don't think we think about the bed surface too often. But that's what we expect to happen. And then it will just continue to bounce off that hard bottom and oscillate back and forth. So what did happen? Here's the column, and we're measuring acceleration and stress. First, I'm going to talk about acceleration. And there's a lot to take in with this plot. So I'll grab my laser pointer. All right. So the dotted lines are measured values, these dotted pink, and I'm measuring at the top, 50 centimeters down, 30 centimeters, 10, and the bottom. Excuse me, from the 10 centimeters from the bottom, 30 centimeters, 50, and the top. And these are time series. So now our axes are flipped. We're looking at time going from left to right. And you see all the measured values sort of peak out, and then the column goes back to rest. The measured values peak out, and then it goes back to rest. We get very little motion at the bottom, and that's not what the wave equation predicts. The wave equation, there's nowhere for that energy to go in one dimension. So the wave equation just predicts this column of snow to be bouncing back and forth forever. So that's not a very good model. Let's look at stress. Again, we have the dotted values or measured values, and the solid green line is the wave equation. As a boundary condition to the wave equation, we say, let's put in this stress wave that matches what I measured. Not making any stress measurements within the snow, but the wave equation is predicting an increase in stress because of that reflection off the bottom. And then you get quite a bit of stress at the bottom, which is larger than what I measured. So right here, it's no good because the modeled stress is like 1.5 times that of what I measured. So the bottom line is that the wave equation wasn't good enough to model stress wave even through a hard slab. This was like, I think the density was like 320, pencil hardness, pencil plus, and there was so much attenuation or damping that even in 60 centimeters, the wave equation wasn't good enough. So what to do? We need to have something in the model that accounts for air squeezing through the pore spaces, bonds between grains cracking and straining a little bit, heat being generated, entropy increasing, all of that stuff that we don't have a perfect system that's going to be described by some damping. And so there's an equation called the damped wave equation, which looks just like the wave equation, but it has one more term here that is damping. And B is the damping coefficient. A higher B means more damping or more attenuation. And this B term is inversely proportional to viscosity. So higher viscosity materials would damp less. Remember, viscosity is a resistance to flow. Something like cold molasses has a higher viscosity than warm molasses. That cold molasses is going to transmit energy better than warm molasses. And that's all you need to know for the equation. But actually, one more thing. We still have the wave speed, which is the same, that same elastic wave speed. But then now we have this damping coefficient that's inversely proportional to viscosity. So if we measure what's happening in the snow, we can estimate both the elastic modulus from the wave speed and then also the viscosity from how much that stress wave attenuated. So what does the damped wave equation predict? Like it's named, you still have some stress wave come down from an impact, peaks out there, And then now the dropped weight has bounced off and it's no longer being impacted. And as that stress wave is going down, it's just slowly dying out because of the damping term there in the equation. You still get a reflection off the bottom, and you can still measure a higher force at the bottom than the top because of that reflection. But eventually, it will just die out. So this is more realistic to what we see. So let's look at that same drop. And now we have the same impact from that same column. I'll grab a laser pointer again. And the solid purple line is the damped wave equation. The faint purple line is the wave equation. And then these are the same measured values with the dots. So you can see that the damped wave equation over time, we get that acceleration, deceleration, and then it stabilizes. Acceleration, deceleration, stabilizes, and so on and so forth. And it matches the measured data a lot better. Likewise, with the stress, drive the model with this impact that we measured. The model predicts still some reflection off the bottom, so still a slight increase in stress as it's going down from that reflected bottom. But now, when we get to the bottom, the model matches the measurements. So that's describing the behavior pretty well. So I did a handful of different densities and impacted these columns like 50 times and made measurements for what that elastic modulus and viscosity are. Because if we can come up with relationships between density, hardness, temperature, and those model parameters, then you could drive a model into different situations. Like say you had a wider column, say you had different layers. Having a good relationship between snow properties and model parameters, that's how you would drive the model. So here's elastic modulus versus density. On the vertical axis is elastic modulus, horizontal is density. The different colors are just different temperatures of snow. And so as you get denser, you get stiffer columns, so nothing groundbreaking there. And these values match up with how other people have measured elastic modulus in snow. And then likewise with density, those denser columns, so now we're looking, or with viscosity, now we're looking at viscosity. The denser columns are more viscous as well, and so that's less damping. Those hard slabs should transmit energy better than the soft slabs. So, in conclusion, the slab and the bed surface properties matter for fracture initiation. The slab and the layering of the slab will kind of describe how much that stress bulb is attenuating or damping. And then the bed surface matters because if it's a really soft bed surface, you won't get much reflection off of it. Whereas if it's something really hard, like rock or an ice lens, it's like being tackled on concrete versus being tackled on a soft mattress. Even hard, dense slabs attenuate stress significantly. So much so that in just like half a meter of pencil hard snow, the wave equation doesn't do that great of a job describing it. But the damped wave equation does a better job. And so next steps I have are to expand into 2 and 3 dimensions. This was all with compression test sized, but I'll be doing stuff with extended column tests and also applying it to some field data. So thank you to Doug and the Yellowstone Club. I was up there dropping weight on columns of snow and extended columns of snow and then not isolating the sides and measuring the acceleration of all those. And so the model's not at a place yet where I can apply it to that data, but I look forward to applying the model to that field data. And then last, many of you know this already and you've participated in this study, but I'm working with a Norwegian grad student named Håvard Larsen, and we're measuring how hard people are tapping on their tap tests. And I've got the tapometer back there, so during breaks and lunch, I'd be happy to see how hard you're tapping. And lastly, thank you very much to Ladine McKittrick, Chris Borstad, Carl Berkland, Ed Adams, and Mark Oakes for their serving on my committee and helping out with this graduate research. And thanks to Kevin Hammonds in the Sub-Zero Lab, where I'm doing this work, Yellowstone Club, and the American Avalanche Association. Be happy to answer any questions.
So when you get the bounce off the really hard bed surface, it's in the field, oftentimes on top of that really hard bed surface, we have a lower density weak layer and then our slab over it. That's what we're concerned with. I'm wondering what your thoughts are on what's happening to that wave if it encounters a layer of lower density before it hits that. And I would expect it would just attenuate a lot more.
Yeah, that's a great question. I don't know. I haven't made the measurements with weak layers, and especially thick weak layers. But those softer materials and more porous materials wouldn't transmit the stress wave as well through it. So it's still going to transmit some energy, I think, through the weak layer, especially before it's cracked. You know, it's like maybe right under your impact, it's cracking right immediately, and all that energy is going into the crack initiation. But the size of that crack on the edges, maybe you'd get a wider crack, but that bed surface, yeah, would still be reflecting it to some degree if all the energy hasn't gone into cracking it initially. But that's a good question, and I'm just speculating. I don't know. I haven't made any measurements about that. Yes.
I noticed in both of your measured data's or presentation, it had here was the general wave, but then there was a high frequency wave kind of on top of that. Do you know do you have any hypothesis about what that might be caused by, or maybe that's part of the 2D, 3D investigations?
There's just some noise in the data, first of all. Like, those accelerometers only have a certain resolution, and so if you're in between accelerations, it's going to bounce to one value or the other. But then you can model that impact as a really smooth wave in theory, but then in reality, you kind of have different waves all stacked up on top of each other. And so those high frequency, the short duration aspects to that, like of that smoother wave in general, maybe you'd pick those up as well. Did you want me to bring up those figures?
If you want to look at it, but no, I was just curious. Yeah, I think it's probably something like that. It could be something at the very crystalline level. Who knows, where it's not as monolithic of a structure as concrete or metal or something.
Mm-hmm. Yeah. Yeah.
Your snow column was uniform; it wasn't layered. What is your hypothesis for if we had a layered snowpack with, kind of softer snow up top, denser as we go down? Like, would that the wave wouldn't necessarily be completely smooth and uniform like you were showing, even in the dampened? Like, you could measure that. Would it jerk around a lot? Would it be moving around, or would it stay relatively similar like the model showed?
It would change as it goes through different layers. So like now I don't want to mess it up, but like you get a different situation of a hard slab over a soft slab versus a soft slab over a hard slab, depending on that orientation, even if they're the same densities and same material properties. And I think that's as far as I'll say, because I'm blanking on which one would deliver more stress to the bottom. But yeah, the orientation of the layering would matter in this model, and yeah, those properties would matter as well.
And what are some practical implications of this? Like, when you're done with your research and you've shown the dampened wave works, or however it, like, how do you see in years moving forward that would translate into our understanding, or on a practical level as we're going out in the field?
Yeah, good question. I think the stability test, translating the difference between a compression test and extended column test and roosh block, and then these tests to an actual avalanche started from an impact. A model like this could tie all those together, and you could have an answer, because we all know that hitting the top, you're not hitting it as hard as like a skier is hitting the top of the snow or an explosive, but both are breaking weak layers, both are propagating cracks. And so the extent to which you're focusing that stress in your isolated column, I think this model could give a good answer to that. And then moving forward kind of down the road of like having simulated snowpacks with the model snowpack, you could have simulated responses to different impacts and maybe some red flags for this slab is really ripe for propagating deep stress. And so that also goes into having more nuance and quantitative answers to how deep a snowmobiler can crack a weak layer, how deep a skier can crack a weak layer, etc., rather than just sort of rules of thumb, because it's going to depend on the layering, depend on the bed surface, depend on all that. And so to have more quantitative answers to those questions.
So in like the avalanche handbook with the stress bulb, underneath the skier, that famous little, like that's going to be gone.
Well, I don't know about gone, but like updated. It's sort of the difference between like you're trying to nail a nail into the wood. You could rest your hammer on it and it's this static load. You could even stand on it and that nail's not going to go into the wood. But when you hit it, it's way higher force, but just for a really short amount of time. And so thinking about crack initiation as this transient dynamic stress bulb in impact released avalanches and slab avalanches. Naturals, that overcoming of the weight is a different mechanism, but these impacts, I think, could update our understanding of that. Yeah, Carl?
So kind of going back to what Mike was talking about with like a hard slab over a weak layer over maybe a hard bed surface like they see on the south face of Lone Peak or something. But so it sounds like, when you impact the surface and that stress wave goes through and you get to like a less dense weak layer, a softer weak layer, that you're going to dissipate more of the stress, but especially if that stress is now what that stress is doing is breaking the weak layer. But if the stress doesn't break the weak layer, then is my understanding that the amount of stress that's reaching the top of that weak layer, when that gets down to that harder bed surface, then you have this magnification effect off of the bed surface. So you're actually going to have more stress at the bottom of that weak layer than at the top of that weak layer right at that moment. Is that true?
Yeah. I both measured that.
Dissipate too much of the stress through the weak layer. Would that be right?
Right, if it transmitted stress through the weak layer.
Right.
And so it was really tripping me up because in the lab, I was measuring higher force at the bottom than at the top of those columns. So I'm like, oh, are my wires crossed? What the heck is going on here? How could I possibly be measuring a higher force, relative force? It's got the weight of the whole snow above it. But if you start both at zero and just looked at that impact curve, oftentimes I would be measuring a slightly higher force at the bottom than the top. And I think that's explained by this reflection off a concrete floor in this case. But I think you could use the same logic and think about how hard a bed surface is.
Yeah.
And we see the same thing with explosive pressure waves. When they hit a cliff and bounce off, the amplitude goes way up.
Yes, exactly. That's another great analogy, is that like the amphitheater effect, if you're in some rock chute with an explosive, that's going to magnify and reverberate everything, and it's the same phenomenon. Or if you're doing sound for a room like this and you don't have any sort of curtains or anything, you get a lot of echoing in the room. And so it's the same phenomenon, but with stress through the snow. Yeah.
So with in a snowpack, we'll say if there was an ice layer, you know, and say you made an ice layer in the middle of your column, the stress wave, because it's not concrete, so it wouldn't completely be reflected back. Like some of it would go through that ice layer as well. So you've got two things going on, right? Like it's being rebounded back up at a stronger, or you know, because you're saying in like it can like double, you know.
Yeah.
But it's also going down below that ice layer as well, correct?
Right. Yes and no. Like ice isn't as stiff as concrete, so you'd have some reflected, some transmitted, and then this would give a good answer to how much bridging matters and that sort of a thing. Is how much that stress just goes across that really hard layer versus continues down if there's something softer below it. And so with a good working model, you could simulate those different scenarios of different thicknesses and hardnesses of ice lenses. But yeah, I don't know. Yeah, it's interesting. Yeah.
She's been out there for a while, sorry.
It's all good.
How much would you expect, and maybe Ed, in the field, you're going to get, when you apply your pressure to the surface and you have all this energy going down, but then you also have slab bending. How much energy is going into bending this, or is dissipated by bending the slab versus the static thing that's just going straight down? You know what I'm saying?
Yeah, totally. It's a great question, and it's something that I'm planning on integrating into this stuff. And I think that the slab, both are fast. The whole thing's fast. The avalanche initiation's fast. But this stress wave, that's moving at like a kilometer a second. And then the bending is a slower process, and the crack propagation is a slower process. So in sort of my head, yet to be tested, is that you'd have this sort of three phases where you have stress wave transmission, gets to an initial crack, and then now you have that crack, and then it's slab bending that's driving the propagation. But since it's a relatively slower process, the stress wave's already out of the picture, and now you have this slab bending and driving the crack. So it's a sort of different mechanism, and then I think the governing equations for that would be beam bending and plate bending and those sort of mechanics.
It's all in the plans.
Yeah. Yeah.
Then what are you going to do about variability?
Yeah, Carl.
So
It's like defending your thesis. You're getting your thesis.
So instead of saying, well, the skier's on the snow surface and they're bending the slab, and then that bending of the slab is breaking the weak layer, it's more like the skier's adding stress, the stress is breaking the weak layer, and the broken weak layer then is contributing to the bending of the slab, which then propagates from there.
Exactly. That's the theory that I'm putting together. Is that
It's an egg and like a chicken and egg question, right? You don't know which one for.
Yeah.
So for the crack size, that would be a strength-based criterion. You'd have some strength of the weak layer, and if the stress exceeds that, then you have a crack, and then the propagation is a critical crack length question and slab bending question. So yeah, sort of in theory teasing out those two mechanisms as separate mechanisms, but yet to be confirmed with experiments. talk to me in a few months, and maybe I'd have some data to show that.
Is this master's or PhD?
PhD.
Yeah, seems like it.
It's a senior project.
Okay. And